Hi everybody, this is Jacob Peitzmeyer here, and for my screencasting assignment, I was going to do mine over the Pythagorean theorem. And mostly I was going to look at probably my two favorite proofs of the Pythagorean theorem, and you'll kind of see why they're my two favorite here shortly. So a little about proofs of the Pythagorean theorem. What I think is just really cool about the Pythagorean theorem is that it's been proved over 100 times, by hundreds of different people. And I just think that's so cool that there's just people who have, just got out, tried ways to prove the Pythagorean theorem and done all different types of methods to do it. And that there have been some very famous mathematicians who've done it. There's been a president who's done it, which is going to be one of the proofs. There's even been some of the teenagers who's done it. I know Albert Einstein did it when he was just a kid. And they've all done it just completely different ways, but gotten the end result in that a squared plus b squared equals c squared. And I just think that's just so awesome. So James Garfield proof, I was going to start with that one. I'd say it's one of my favorite proofs just because I'm not too much of a political person, but I just think it was really cool that there was a sitting president at one time who just, did prove the Pythagorean theorem the way that he did. So this is the only proof made by a U.S. president, sadly. And he made the proof in 1876 while he was actually in Congress, and apparently he just quoted as did it being for fun. He was just, in Congress, let's just do some math and prove the Pythagorean theorem. And he even studied mathematics even while in Congress. And it's too bad our politicians don't do that much more now, but they probably have more important things to study than just mathematics. So he kind of uses a trapezoid to prove the Pythagorean theorem. So if you look here, this is the kind of the trapezoid he uses. So it's the trapezoid. You have the top, which is A, the bottom is just B, and there's an a squared, an ABC triangle on the bottom. There's an ABC with the base is A on the top, and then if you see, there's a C by C triangle. Kind of there in the middle. So you see, there's three triangles. That would actually be an isosceles triangle. So here's kind of the proof. So he wanted to do it two ways. On one side of the equation, he wanted to add up all the areas of the triangles, and then another way he wanted to do it is he wanted to use the area of a trapezoid and set these equal to each other and somehow get a squared plus b squared equals c squared. And the reason I really like this proof is that area of a trapezoid is something that you do in geometry. It's something you teach that you just add the bases together, multiply by the height, and divide by 2. And that's actually something I'm teaching my geometry students, I think right now. I think I just taught them that yesterday. We did some problems like that. Fortunately, I didn't teach them this, so I think it would have been cool if I did. So the area of the trapezoid is, like I said, half of adding the base scalar times the height. So if you look here, it's going to be half of adding the base scalars A and B. So the base scalar is going to be A and B. If you have to look, the height is also A plus B. So it's going to be half of A plus B times A plus B. So if you just double distribute that out, you should get A squared plus 2AB plus B squared. And since it's half, you're going to get left with half of A squared plus AB plus half of B squared is what you're going to get when you do that also. And so then the second way he wanted to do it is that, well, if you see there's three triangles, and the area of a triangle is just length times width divided by 2. So that was the other way he did it, and since they're right triangles, it's super easy. So you're going to get A times B divided by 2, A times B divided by 2, and then C times C divided by 2. So you get half AB plus half C squared once you find the area of those two. Now, again, this is just finding area of that trapezoid just in two different ways. So he said, well, they have to be equal to each other. They're the same shape. So half of A squared plus AB plus half of B squared has to equal half of AB plus half of AB plus half of C squared. So what I did is I just multiplied everything by 2, and then I combined those half ABs together. So it's going to get A squared plus 2AB plus B squared. If I combine the half ABs, that's just AB. And then multiply by 2, that's where I got the 2AB. And then half C squared times 2, and then C squared. Now, there's a 2AB on both sides of the equation, so I subtracted 2AB out, and what am I left with? A squared plus B squared equals C squared, or the Pythagorean theorem. And that's what our sitting U.S. president did for fun while he was still in Congress. And again, I really just like this proof because it really makes sense. You're just finding the area of a trapezoid, using the rules of a trapezoid, and then you're finding the area of that trapezoid basically by doing each individual triangle, and then you're just, logic, they have to equal each other, and then just reducing and getting the Pythagorean theorem. which I think is just, I don't know, it's just kind of cool to me. Now, the second proof I want to do is actually Pythagorean proof, which is kind of where Pythagorean theorem comes from. So, the Pythagorean theorem was known for a while. So, like, people knew, I think they saw that a lot of like ancient Egyptians knew the Pythagorean theorem and saw like they knew about it and used it in buildings and stuff like that. But Pythagoras was kind of the first one to prove it, even though it was known. He was the first one to lay out a proof and said, "This I can definitively say, mathematically, this is why it is true." So Pythagoras made this proof by creating a square and rearranging it. I think it's a proof by rearrangement is kind of how he did it. So if you kind of look here, here's a square. And then there's kind of 4 triangles on the outside, all with length A, B, and diagonal C. And that makes a triangle, or not, sorry, it makes a square on the inside that is all length C. And you know these are all 90 degrees because if these are all the same 2 angles. So if one of the angles have to add up, angles inside of a triangle have to add up to 90. And if the 2 are next to each other, they have to add up to 90. And then that one in the middle that has to be with the square has to be 90 also. So you know that's a square. And he literally just rearranged it. I don't know how he would have done that back then, but he just rearranged it. So he took the two triangles, put them together, put them on one part of the square, took the other 2 triangles, put them together, and so it actually made 2 squares instead of one big square, C squared. And then you notice that the squares have length, one square has length B by B, so B squared. And then one square is going to have length A by A, so its area would be A squared. So then he obviously figured that, well, if the square in the middle is C squared, then I can divide that up into A squared and B squared. That means A squared plus B squared has to equal C squared. And again, this is something that you can do mathematically also. So one way is to do it by proof by rearrangement, kind of like this. And then there's the proof by actually doing it. So it's kind of continuous with Pythagoras' proof. He looked at that first square and thought, okay, the height is A by B and the length is A by B. So it'd be A plus B times A plus B would have to be the area of the whole thing. So again, almost exactly kind of how we did the proof by the trapezoid, which is kind of how a lot of these Pythagorean theorem proofs go. So we took A plus B times A plus B, obviously, A squared plus 2AB plus B squared, same thing we did last time. And then you can do the proof, you can find the area of that square by parts. So you can find the area of each triangle. So, there's 4 of them. And then the square also in the middle. So, of course, just like last time, it's going to have, all the triangles going to have a height and width of AB. And the area of each one's going to be half of AB. And since there's 4 of them, the areas of all triangles are going to be 2AB, and since there's that square in the middle, that's C by C, so that's going to be C squared. So then I find the area of the square by parts, by adding that square with all 4, is going to be C squared plus 2AB. And just like we did with President Garfield's proof, this is basically finding the area of a shape in 2 different ways, filled with triangles and other stuff. And then we can just set them equal to each other because the area has to be the same regardless of how you got it. So, just like we did last time, these 2 areas must equal each other. So then we can say, well, A squared plus 2AB plus B squared, which is how we got the square as a whole, has to equal C squared plus 2AB, or we're doing it by parts. And then this one's a lot easier. You can just go straight to subtracting 2AB from both sides. So then you just get left with A squared plus B squared equals C squared, which, again, that's just Pythagorean theorem. And so if you kind of notice, these proofs are not really the same, but they're very, very similar to how they kind of prove it. You're finding the area of first one, you find the area of a trapezoid in 2 different ways, set them equal, and then you get the Pythagorean theorem. And then in this one, Pythagoras' proof, you can rearrange it, or you can find the area of a square in 2 different ways, set them equal to each other, and then boom, you get Pythagoras' theorem, or Pythagorean theorem. And I would say that these 2 are my favorite, like I said before. Probably more so the Garfield's one, just because it's something that I think students could actually do, or they could watch and it would actually make sense. I know there's a lot of proofs of the Pythagorean theorem, and just proofs in general that don't make sense, and I think proofs is one thing that students really struggle with in geometry. So I think it's just really cool if they could just watch these. I don't think they could probably figure it out on their own, but just watch it and see how they, using the skills that they've learned in class, show that the Pythagorean theorem, which is something they've known probably since middle school, is how a lot of people back then, or just in the 1800s or way back then, proved it. All right, thanks guys. I hope you guys have a good day.